Hi everyone, my name is Abner Zárate and today I'll be presenting my poster that's named Microwave-Assisted Synthesis of Nickel, Magnesium and Aluminum LDH and its Electrophoretic Deposition for Electrochromic Application. It is presented at the 8th Symposium of the 29th International Material Research Congress. Starting with a little introduction, we see that nickel oxide is the most used analytic electrochromic material. This is because it has a lot of properties that allow it to be applied in this field. Despite that, it also has some disadvantages that make researchers choose another option. Recent investigations show that if we obtain metal doped films of this material, we can improve its electrochromic properties. However, the processes by which such films are obtained present certain problems. One way that could allow us to avoid these disadvantages is to use a precursor as an alternative in the process to obtain such films. Here is where LDHs appear. These are some type of inorganic clays whose properties allow us to form deposits, which can lead to metal-doped metal oxide films when thermally treated. This is why we propose a route where we synthesize a nickel, magnesium and aluminum LDH through a microwave-assisted process, then we carry out an electrophoretic deposition and thermally treat the obtained films. Our hypothesis is that the magnesium-aluminum doped nickel oxide films obtained through this process will have better electrochromic properties than those of the undoped material. Our methodology consisted in selecting the doping proportions to work with. Later, we made different solutions containing the metal ions and adjusted the pH with sodium hydroxide. We took said solution and subjected them to the radiation of a conventional microwave. We separated and dried our products to disperse them in different solvents and then carry out a series of electrophoretic deposition. At the end, we thermally treated our films and tested their electrochromic properties. As the results, we first show the particle size distribution of our three materials in the three solvents tested. As we can see, the isopropanol was the best solvent, because it's the one that led to the formation of a dispersion with a better homogeneity of the particle size. It also had a César potential in the optimal range for an electrophoretic deposition. Here we present the X-ray diffraction patterns of the three samples, under powder form, after deposition, and after the heat treatment. We can appreciate that once synthesized, our material had both the LDH and the nickel hydroxide phases. This can be due to the low amount of aluminium that was in the synthesis matrix, which acts as a limiting reagent in the formation of the LDH. After being deposited, we can see the peaks corresponding to our substrate in both the LDH and in the nickel hydroxide. However, we notice a decrease in the intensity of those corresponding to the hydroxide. This tells us that the charged surface of the LDH makes the EPD have a preference of its deposition over the nickel hydroxides. Lastly, the diffraction pattern of the calcium sample shows a decrease on all of the signals, but we can see those that would have been expected from the nickel oxide. We conclude that the thermal treatment decomposes our material but doesn't allow it to properly crystallize. On the same images of the deposits before the thermal treatment, we can appreciate their homogeneity and abundance. After the heat treatment, we can see that a sintering process has occurred. However, the abundance of the doped deposit is still greater than that of the undoped one. On the last picture, the morphology of one of the materials is shown, it being the typical one of the LDH. Lastly, we present the result from the electrochromic test. On the left side, we can see the transmittance of the nickel oxide films, both in its colored and bleached states. It can be appreciated that all of the films show a lower transmittance in the colored states and a higher one on the bleached one. On the right graphic, we compare the change in the optic density of the films, and we can see that out of our three samples, two of them have a greater optic change in the visible region than that of the undoped material, confirming our hypothesis. As the conclusion obtained from this work, we conclude that the microwave-assisted synthesis led to the formation of the nickel hydroxide phase with the incorporation of our doping metals in the LDH phase. Isopropanol is the best solvent that produces the best dispersion and leads to a better EPD. We also conclude that the EPD has a preference for the LDH over the nickel hydroxide, and that the thermal treatment leads to a sintering process. Also, two of the metal-doped nickel oxide films have better electrochromic properties than the undoped one. However, further research is required to understand why the other doping condition didn't show this improvement. And that's it for this poster presentation. If you have any doubts regarding this investigation, feel free to contact me through my email. Thanks for listening.